Oh, it says we're alive. Hey guys, what's going on? Memes here. Yes, a few days late. Probably a couple of chocolate bars short, but that's okay. Because today we're going to be talking about the Planck temperature, the limit of temperature as we know, it, according to physics. As we typically understand and have calculated from the standard model of particle physics, etc., etc. Okay. So today we're going to be going back because we're going to be talking about coherent units, natural units, if you would. Is there a difference? Well, coherent just means it's going to line up via the different transforms and everything based upon my knowledge. Natural units are basically what we're going to get out. Now, if you could use natural units that are coherent, maybe I'm just babbling on and this all means the same thing. Possibly. But again, with our running little Planck series, we're going to go over to our friends here. All right. Again, the links in the doobly doo. Feel free to take it for what it's worth. Again, this is Wikipedia. Occasionally, you will see some synthesis, and occasionally you go to links. Oh, let me. Okay, well, this link is dead here. Now, it doesn't mean it doesn't exist, but uh, again, when you pop into like some of the behind the scenes Wolfram design tours and everything, and they're just looking for a first level approximation. Well, what are people saying about this? What do mathematicians say? What do folks in category or whatever? They're saying that they'll go there, and I've seen them literally check Wikipedia. It's like, all right, that kind of sounds like the general gist of things. And if the folks from Wolfram and Wolfram Alpha are also the things that run Alexa and Siri, aka Wolfram Alpha, the computational knowledge engine, um, that's my justification. Take it for what it's worth. Again, trust but verify. As we can see here, our Planck units. The whole thing is, look, we're basing it off of one. Ever since I had that conversation with that about what is one, that successor. It's just our reference. Our reference of the thing that we help the user count. Why? You take a piece of chalk, you put a tally mark, you got your one. You put another one, that's a two there. Now, that's a very rudimentary way to explain things. Learned that from Professor Norman Wildberg. He angers a lot of folks in the mathematical community, at least for a noob on math like me. Couple hundred episodes help me at least get a framework. Again, I ain't a mathematician or anything, but I'm a dude on the internet. Today we're going to be talking about the Planck temperature because generally, and again, this is going to be a bit ad hoc. Ad hoc again, trust but verify. Uh, and again, please correct me when I spout hot garbage. But the whole concept here is we're having some form of a unity because you get your scale here. It's like, all right, you get the Planck energy, the Planck mass. What happens? Well, Planck mass times c squared, E equals mc squared. You're going to get the Planck energy. Why? So the interesting thing is c squared within our units, it's going to give you a factor of like 10 to the 16th. So we can just do that right here. So we're just going to Wolfram alpha, c squared. We're going to have to specify it's a unit. All right. So aka small c squared, the speed of light squared. All right. It's this ginormous number here, 10 to the 16. Okay. So the Planck mass in and of itself is just, it's actually very small because on our reference scale, we're about a meterish, maybe, I don't know, like around the 100 kilogramish range, something like that. And again, magnitudes. That might be about 20 pounds for us imperialists here in the States, but typically you don't find many, at least fully grown humans, that are like 10 kilograms, because that's basically the size of a large dog, like 22 pounds. 1,000 kilograms, maybe there have been some humans that have weighed around that. It's might not be the healthiest thing to weigh over a ton, but then again, ain't anybody's dad. So, again, on our scale, example. 1 cubic meter. If you literally took a yardstick and actually no, you take 8 yardsticks, you glue them all together in a particular way. It basically, if you had a 1 meter cube and you were to fill it with water, you're gonna have about 1,000 kilograms. Why? That just happens to be. Well, originally we did kind of base the definition on the kilogram on a cubic deciliter of water, and even Wolfram Alpha was like 1,000 kilograms. That's it. Oh, okay, so it's of magnitude of a dairy cow, 700 kilograms. I did not know that. Okay, average American dude is about 90 kilograms. Okay. So basically, assuming the conventional density of water is a thing, basically, if it's pure water, it's going to be just a hair under it, like a little dash, a pinch of salt, which most water on Earth is probably a wee bit salty. And again, at a given pressure, because water is interesting, because depending on the temperature, it will actually expand. But basically, right around, I think Rick said it's around 39 degrees. I had looked into this, and I was able to squeeze out a bunch of decimal points. If you add a pinch of salt and you have the right conditions, basically, 1,000 liters of water, aka 1 cubic meter, can be 1,000 kilograms, which is really cool. It's just that's just something that you pick up on, and even just going through all of like this like data and the history of units and stuff like that, it is quite interesting. It's like, wait a second, that actually kind of gives the meter and the kilogram some form of relationship there. Don't that just beat all? Speculation aside, let's go back to our friend the Planck mass. So the Planck mass on our scale of the kilograms, -8 kilograms. What the heck is that? To put it as eloquently as Professor Brian Greene has said on the World Science Festival YouTube channel, approximately the mat of a mote of dust. So you see a little mote, small mote of dust going around. All right, you want to do some magic? You take that 10 to the -8 kilogram mote of dust. If you did some wizardry and you're able to extract all the energy with maximum efficiency out of it, uh, you get the Planck energy, which is Planck energy, of the magnitude of the energy in a lightning bolt. See, this is why a lot of times I view the whole physics, and especially if you're going down like a computational way where you can just type some magic words, and all of a sudden it's like, all right, you go from mode of dust to literally lightning bolt. I'm sorry, I'm again, it reminds me of Dungeons and Dragons. So you get some wizard, they're like reading some some medical point. Word. You're speaking words, some medical point. You're making some signs, some symbols, and then you get to your flip out a reagent there. Okay, made of dust. We get bada boom, bada bing. Equals empty transfer lightning bolt. I think that would make for a cool like movie or game. Maybe I don't know, a graphic novel, something like that. Perhaps perhaps I ain't ready for a Netflix series or something. I feel like there's a lot of ways you could ruin that. Uh, but I think that would be kind of cool. And I think they wasn't it supposed to be Percy Jackson or whatever the thing with Nicolas Cage was, the Wizard's Assistant or something like that. I feel like they were trying to get into that, but I don't think they delved really deeply. Then again, I haven't read enough books, so and again that's a personal take there. Okay, so we're getting the Planck energy. Why am I showing you this? Okay. Well, number one, it was in this little thing right here. All right. So you get your Planck mass, you get C squared, you get energy. Okay. Now, in order to get the Planck energy, well, you need the Planck time and Planck length. They're showing it in this particular version here, i.e., if you were to have a maximum of mass, basically we would typically refer to as a black hole. Personally, I think we should call them mass holes. To be more appropriate, and again, I am biased as a Massachusetts longtime masshole. But as you can see, as your length scale and everything, excuse me, as your mass scale is going up, your Schwarzschild radius is going to increase as well. And it's a 2-for-1 trade-off, which is interesting because apparently back here, if you just there's that two factor there. To calculate the Schwarzschild radius, let's Uh, Here, we can do this real quick because we have a board. All right. The whole conversion thingy for your Schwarzschild. We'll do S W B H. Okay. That whole thing is you got your mass, you got big G, the gravitational constant, and then you got a C squared over here. Okay. Now, to be fair, there's a factor of two here. It's two gravitational constants, or you could just easily say it's factoring in two masses. So if you put the Planck mass in there, eraser go. Oh, it's over here. So I'm a terrible savage. Oh, am I even showing that? Okay. If we put the Planck mass in here, we'll just do sub B. All right. So that's going to equal to length Plancks or Planck lengths, L sub P. I should probably actually start making those big just because it is a name. All right. So for every one Planck mass you throw into a black hole, it's going to go up by two Planck length. You're like, all right, so what's the big deal? The big deal is technically you're going from the densest thing that we know in universe, which is trying to shove a Planck mass into a Planck volume. But coincidentally, rather than having it be one Planck radius, like one may think, just around it, because initially I'm like two, I'm like, oh, well, it's talking about two radii. Okay, so it's talking about the diameter. No, no, this is radius. This is radius. This is the weird thing. This is the weird thing because for every Planck mass, it goes up by two. So that means the thing that's essentially the maximum density that we could try to conceive of gets less dense as it gains more mass. Because that's essentially the point where it's like, all right, well, if you take the mass of the observable universe within approximate magnitude, because we can't account for everything, but we can account for a lot of stuff, apparently. Uh, Basically, if we take the mass of the observable universe, and if you were to shove that into a black hole, you would get a black hole approximately the size of the observable universe. It would explain a lot. It would explain it. Well, at that point, you have at least a reason. Well, why do things seem to be getting big? Why does it seem to be expanding? More stuff is falling in, and black hole gets bigger and stuff like that. Maybe that's Occam's razor. But I hear other smart people saying, no, 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 no. A different type of singularity, even though singularity by its definition is, I think you can mathematically say, oh God, people, someone's getting mad at me, a critical point. And a critical point is literally just a point we cannot define. So, hey, David, good to see you, my friend. Good to see you. Checking on the X side of things, the X Twitters or whatever. They have nothing wrong against like the name X. Who doesn't like having an X in something? It sounds edgy and stuff. I, I went on as the Bird app. It was the Bird app. It's the Twitter because you could say tweet and stuff like that. I'm sorry. I'm sorry. I very easily ADD and digress. But so again, don't trust me. Verify. So just go over here. So there's black. Oh, what do we want? We want the formula. We click on formula. Don't get this is the Schwarzschild black hole. We've never seen a Schwarzschild black hole. It's an idealized form. It's assuming it's not spinning. It has no charge associated. Anytime we've observed whatever we believe to be a black hole, it seems to be spinning. And that's spinning and angular momentum seems to be generating some form of charge. Okay. Coincidentally, randomly, I just algorithmically came into another old video where Ed Whitten in the World Science Festival was saying something about like the Nordstrom solution of black holes and stuff. He's like, why aren't people researching this more? I don't know. I'm just putting that out there. If for anyone, if I ever go back around this, Maybe I'll look into that more at a very short period of time. Okay. So I'm trying to calculate the quote unquote event horizon radius of a Schwarzschild black hole. Do GM. All this is 2, the Newtonian gravitational constant, whatever mass you're throwing in there, and then divided by the speed of light squared. So we go back to our expression over here. We literally just take 2, big G, like mass, divided by c squared. Boom. We get 2 Planck lengths for the radius. Now that's weird. Oh, because they having a phone. Apparently that seems to be required. Yeah. I don't. Oh, this is interesting. Okay, don't mind me. Don't mind me. I'm just randomly playing. It's oh, okay. I'm every once in a while I look at something. Something looked a little familiar, and it's okay. I need to play. Where are we? Ah, sorry. I had a vibration. I wasn't sure if I was going off. Uh, David is asking, how do astrophysicists measure a black hole's electric charge? That's a very good question. To my understanding, they don't. And again, there's upcoming things, but just to the best of my knowledge, that's why we usually use just gravitational based calculations and stuff, and like why we seem to need to have some form of a dark mass effect or dark matter or whatever the heck you want to call it. Because like electric and magnetic things are, as far as like the force is just going around, as far as measuring its electric charge, I don't think we can do that. I think we can just kind of theorize what might be going on. Maybe if we have like a pulsar or something like that, and it shoots a whole stream of highly charged electromagnetic things, maybe we could calculate. Oh, that's actually let's black hole charge measurement. This might actually be where equals the charge of all matter create. This is actually how can electromagnetic field escape? The event horizon. Well, technically, aren't we saying it's around it? Three quantities inspired of black hole mass, angular momentum, and charge. And the first is easy enough to determine. Look at the gravitational effects. You use the short-tried formulas, compute the mass. Angular momentum being found in the cool little ergosphere Penrose discovered. However, I don't know how to determine the charge of a black hole. How can an electromagnetic field escape the event horizon of Reisner neutron black holes? Is there any experiment? Ah, see what do we got for the top answers. This produces an electric field. In fact, rate distance is much larger than the horizon. The field strength. Okay, so it's just your standard. Wait a second. 4 pi epsilon not. Wait a second. The, okay, we just got r squared there instead of h bar. And if that was charge squared, that would be the formulation for the fine structure constant, or at least if you had elementary charge there. Or the best answer is that it doesn't. It was never in the horizon to begin with. Okay, okay, it's formed on the surface. Um, by electric field, even though it travels. This is wow. You're getting back to Anastasia's question of what the heck is charge? Wait, we're talking about calculations there. Measure. Okay, you would need to look at. Okay, that's okay. I'm pretty sure we don't measure that. I think we're just using the gravitational effects and the standard cosmic distance ladder to try to piece together different things. Yeah, and also I'm like, I think when you say charge, it's does it itself have charge, or if it just has angular momentum, is it generating charge from all the other stuff around it? Because as long as the stuff is moving and you have charges in relation to each other, I think, yeah, I think that'd be really hard to measure. Because what is it? We think we technically just measured our Earth's electric field. That sounds like a weird thing. And you're like, well, duh, of course that's a thing. But, oh, we talk about the Earth's magnetic field, but it's the magnetic field might be, hold on. Earth electric field measurements. No, okay, yeah, this is last year. Not to just goes a long shot global electric field. Wide electric field to be a fundamental aspect. So, you know, those things like that. Yeah, basically we know this has to be a thing, but okay. If we just measured the Earth's electric field, I'm assuming that, and again, in a big assumption, we probably never actually measured the electric field of a black hole. Yes. Like that's where it's like it's easier to point something back towards Earth. And again, some people would disagree with that in the space. Hey, I don't know. I don't know. That's it's Occam's razor says, I don't know, maybe it's kind of a ball. Earth might kind of look flat, but stairs seem to be a thing. That's best thing. There. Why is it so dark and everything? Ah, yes. Actually, I finally watched one of those things where it was from the Math and Science channel. It's like, did we really land on the moon? And I'd watched like the 2 minute short, and I'm like, this is the best explanation I've ever heard. But then again, I also don't spend a lot of time on these things because it's like, okay, well, number one, if the Earth was flat, cats would have pushed all the stuff up, pushed all our valuable things off the sides. Number two, if that was the case and there's a big ice barrier, well, if it's starting to melt, then well, we have to stop global climate change. Then, and well, I tend to think some of the folks that maybe supporting general perceptions may be against other perceptions. But then again, I don't know. Uh, basically, that generated. At one point, they said, "It's like, well, why don't we see stars?" It's like, well, the sun is out right now. Do you see stars and stuff during the day? The best part is if we never landed on the moon, the Russians would have called us out. How do you argue with that? The amount of trolling that we do to each other. Oh God, the propaganda would have been obscene. So I'm like, that actually probably is the best thing. Whatever you want to say about the science, yeah, if we were making that up, yeah, the Russians would have called us out right away, and vice versa. So that's the ultimate justification for us actually being on the moon. That the most compelling argument, aside from all the science, believe whatever you want about the science, the Ruskies would have called us out. Literally within the parameter of today's internet and call out culture and everything, that actually probably is the most compelling argument. But back to the Planck temperature. I'm sorry, I've been digressing for about half this episode. All right. So one of the things you can tell is basically you need Boltzmann's constant. All right, let's go back into what it is. All right. We can actually just scroll down because it's in the same thing. So the Planck temperature, it's this crazy thing right here. So as we can see our standard things, we're taking the square roots. We're taking radicals. Why? Well, because sometimes you got to be radical to try to figure out what's going on. Kind of like what Max Planck did. It's like, why does this keep diverging to infinity? What would we need to put in here for it to work? I don't know, like 91.18. nanometers or whatever it was, wavelength, aka you get Planck's constant, aka h bar, 10 to the minus 34 joule seconds, whatever the heck that is. Energy times time leads to action. Energy, time, all right, it keeps going. I know I liked using well, action is kind of the difference of force because force is basically just mass distance divided by rate or time squared, whereas action is mass area divided by just a single time component. It's amazing what you can do with just time and distance. Why does it work? I don't know. It's magic. Any significantly advanced technology is indistinguishable from magic. I don't know. I occasionally have heard, oh God, was it Professor Loeb? I feel like it was the Professor Loeb thing. Maybe if I'm misattributing it, I apologize, but something about the alien or the grand alien designer scientist in a white lab coat. The scientist in the white lab coat paradox. Where are we just made? I don't know. It was to say if we're gonna go down that road, hey, maybe we're just a science experiment. Is it divine? Is it Maybelline? I don't know. But the Planck temperature, as far as we know it, after my diatribe, basically it's this: we've got our radical, and we've got our three main components. What are our three main components? Well, we just look at what's in each of these things. Each of these things, it's got h bar, Planck's reduced constant, the elementary unit of action. All right, we got our big G, the Newtonian gravitational constant, the constant of gravitational proportionality, whatever the heck that might be. There. And we got C, the speed of light in a vacuum, aka the medium. Uh, we got different components of this. So we've got action, we've got volumetric acceleration, and we've got the maximum of speed. Okay, so these are limits to reality as we know it. And we mix them together. And then if we want to get charged like we did before, basically, long story short, you gotta plug in the electric constant somewhere. So whether you want to parameterize it like this with the 4 pi or this without, again, I argued with this out of bias and everything, the way that Thad showed me, and this is when the Planck mass and this basically it's. We'll just show this real quick. So basically, if you do big G, so Newtonian gravitational constant, if you take your all, hold on, let me go back up here. It's I think this is a useful exercise. Also, number one, as somebody that doesn't have a degree in physics, every time I at least go through this and try to understand it, it helps me. So basically, the whole force thingy, mass one, okay, big G, mass one, mass two, divided by your radius squared there. Okay, so if we literally just go in there, big G, all right, I'm gonna do blank mass, blank mass, the blank mass times the Planck mass all over a length, a radius squared. So we're just going to do Planck length because we're using Planck units. Okay. Unit. Okay. So bada boom, bada big, it equals the Planck force. All right. So that was using mass. So instead of using mass, we used another constant or proportionality, Coulomb's constant. That's the thing for the proportionality of charge. So we do the exact same thing. We just put in charge. Charge. So I'm from the Boston area. That's how it goes. Yeah. 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 You park your charge with Coulomb's con. Yeah, it doesn't sound as good as park your car in Harvard Yard. But long story short is it unites with the Planck force right there. And again, that's my justification for using that one. But the interesting thing is, like charge, we do need another constant that is not our standard three. Our elementary unit of action, our unit of gravitation or volumetric acceleration, and in respect to mass, um, and then also the maximum of speed. Okay, what's different here? This is Boltzmann's constant squared. All right. Why? Why? Well, because we're taking a square root. So if you got temperature squared there, um, and you only want one dimension to come out that we could report as a thing, you need to take the radical. Because again, remember, this itself without the radical gives you area. If you take the square root, aka Pythagorean theorem, rather than an area, you just get a single length. Which raises a whole bunch of other questions about, okay, well, if that's fundamental. Well, if you were to take that seriously, one might have to conjecture that, I don't know, maybe mass squared is fundamental. Wouldn't that be weird? Or have we seen something like that before? Then you could have time squared, whatever that means. Well, time is a very interesting thing. Hopefully, we'll be talking a little bit more deeply on it in the future. Okay, but again, half hour into our broadcast, let's actually get to what the heck temperature is. Okay. Temperature. It's just energy in a particular form. Kind of like charge is energy in a form. Mass is energy squared, usually in that type of form there. Thank you, Professor Einstein. But this is Boltzmann's constant. Why is Boltzmann's constant? How does this work into our initial thing? We were showing the Planck energy up here and saying that this is important. How do we get to this? How do we get to this from temperature? Temperature is nowhere on here. Okay. Oh, they have time up there. Okay. Helps when you actually look at the whole diagram. It's a noob. So let's duplicate this. So then we'll go back. Okay. All right. So we got the Planck mass and c squared. All right. So that gives us the Planck energy. So how do we get this to temperature? By the magic of Boltzmann's constant. I forget which way I need to set this up here. Hold on. Multiplication. Well, seeing as Wolfram Alpha is telling me there's no way to interpret that, think I divide the Planck energy by Boltzmann's constant. I could be wrong. Nope, it was this way. I divide by Boltzmann's constant. Ah, okay. And again, I did a project on onions. I still get confused. So, long story short is, let's go back. Okay. So we got the Planck energy within our dimensional units here. And again, we're using, you can argue about, but within our base, kilograms, meters, seconds here. Basically, it's get that 10 to the 9 exponent is going to be what's happening. And Boltzmann's constant is like 10 to the minus 23. Man's constant, like 10 to the minus 23 joules per Kelvin or something. Yeah. Okay, so you got 10 to the minus 23. So, long story short, is what's happening over here. This is 10 to the 9. So, if you're dividing by a wicked small number like 10 to the minus 23, basically you end up adding that exponent. If you're dividing by a big number, it would get smaller. Since you're dividing by a really small number, it gets bigger. So since this is the ninth power and the other is minus 23, basically you add in 23. So 23 plus 9 is 32. Hence, when you divide this whole thing, the Planck energy, hold on, let me put little brackets here so it's a little less cluttered. Okay. So we got our Planck energy up here. Mass, c squared, thank you, Einstein. Divide by Boltzmann's constant. Oh, it's giving this 10 to the 32 Kelvin. Wow. That's pretty interesting. Now, again, this seems like a simpler way to express it. However, remember the Planck units are set up as we're just trying to use uh, the speed of light, the elementary unit of action, and big G, Newtonian gravitational constant. Like we're just trying to use these three things and define it. That sometimes beggars the question, why? And again, if we're going to go this convention, well, these are radical. Are these fundamental, or are the non-radical versions fundamental? During the Wolfram Unit project, there's a very interesting thing that happened. Even when you're taking their scaling factor there, for most of these things, it seemed to come out to reasonable values that, okay, I could try to start to at least attempt to justify. For the Planck tower, it didn't work just by doing that scaling factor. The interesting thing was, now the Planck tower is Planck energy per Planck second, or Planck time. I like Planck second because Kali said Planck second, and it seems to work. So, Planck power. This is interesting. This this is basically doesn't have an elementary unit of action. It's basically one above the Planck force because the Planck force is c to the fifth divided by big G. So, excuse me, to the fourth divided by big G. It's gonna unit. Okay. So this is the Planck force, but if you raise it, the c raised to the fifth power, it goes to uh, unit goes to the Planck power. All right, it's a very ginormous number. Now note, this is not a radical. Right? Well, number one, I don't think it's going to line up because these units should be different. We need a unit. It's giving us root dimensions and stuff like that. Okay. Occasionally, now here's the thing. Occasionally, there are interpretations. Now, again, this is not me. This is Wolfram Alpha. If you do square root of, again, need to codify this unit again. Still no standard dimensions. Uh, but we got Boltzmann's constant squared here. Huh. Well, that's going to have to mean that this whole thing is just going to be energy squared because we're taking the square root of all that, and this is just Planck energy divided by Boltzmann's constant. Let's do that. So h bar c to the fifth. Let's do h bar c raised to the fifth power, and then we're dividing by what is it, big G, I think. Big G, and then let's see, is this energy squared? Oh, that looks like energy squared. Let's take the square root of the whole thing. I only recognize that because I have squared the Planck energy before. Okay. So, all right, Planck it. Okay, so that whole thing just comes out to be energy squared, and we're divided by two Boltzmanns and taking the square root, so we get the same thing we did before. Okay. I realize like, oh God, numbers, this and that. It's like stuff doing things. Am I gonna pretend like I know exactly what that stuff is and the precise things they're doing? No. But for some reason, we humans are being able to get to the point where we're able to quantify observed phenomena, able to do experiments with high level precision to varying degrees of, let's say, inference. Taking a look at what's going on. And as our experiments get better, we get more precision and everything. Because again, it's Lord Kelvin gets attributed with having said, and I'm pretty sure it was somebody else, but something about towards the end of the 18 or early 1900s, like the vast majority of physical law has been discovered. It is simply a matter of determining the significant digits in the sixth decimal place. Now, if it was just that, right about up to the sixth decimal place, things seem pretty chill. Things seem to make sense. Once we got to about the seventh decimal place, things seem to break down, and what the heck is going on? Yada yada, quantum theory, quantum mechanics, quantum field theory. Now we have quantum field theory that has been evaluated, seems to have a precision that has been tested up to 14 significant digits with the anomalous moment of the electron. Cool. And again, I think that's like a single parameter. We may have one or two others that have like 13 or 14 significant digits. Um, a lot of them we have like nine, speed of light, H bar, we got 10 significant digits, epsilon, I think we got like about 10 or so. Uh, Fine structure constants technically measured to 12 with error and like one or two digits there. But then again, depending on the experiment you cite, whether Berkeley or something, there's like 5 to 7 sigma tension. Not sure why. Is that similar to why, depending on how you measure the decay rate of a neutron? There seems to be a strong 10-second difference in whether you're using, what is it, the ion trap or like a bottle method or something. Again, I'm not experimentalist, but there seems to be a specifically difference. There seems to be an observed difference depending on how we perform said experiment. Now, I only became aware of that because thank you, Kali, for pointing that out when I had visited her up in Toronto. I'm like, wait, I heard there was like some variance, but it's like there's a strong noticeable variance depending on, and she said, oh, yeah, there's basically two ways we do it. I looked it up, and oh, I looked at two ways, and there's a significant difference. These are probably some clues about what might be going on. Okay, so where are we going? Oh, I'm sorry, I've been outside the loop. Let's see. Comparing the formulas for the Planck energy and the Planck temperature. I'm not gonna lie. Just, I just popped back over. Hey, Rick. Reckon some person got to see. I literally have not checked the chat in about 15 minutes. Now, I literally didn't notice this comment until right then. I don't know if it's a good thing or a bad thing. I literally just did what you said without even noticing. Cool. To be fair, maybe this was said and just uploaded in my mind somewhere because I'm just looking. I'm like, wait a second. I had a show with Rick about radicals. He stressed the importance of this. Might there be something interesting going on? I had started thinking about this before and playing around with some different. Okay, I looked at something at code editor that had come up. I do the calculation. I'm like, well, this is what it's saying. Why is this important at all? Maybe because it's a non-radical version of something here. Oh, and also to bring things back around that whole thing about within that units project that I did, even if you're taking that scaling factor, that's literally just the Planck flux. And my interpretation is the sum. No, no, we need to measure flux and momentum through the causal graph. Well, your scaling factor is like 10 to the 116. The literal magnitude of the Planck flux is 10 to the 113. You're taking the square root of a ginormous number like that. It's only off on your initial estimate by one order of magnitude. What if the literal flux through the causal graph as a modeling tool is equivalent to the Planck flux? We're saying that there must be flux through it. What if it was? And again, even if there is anything to that, it is highly speculative. That was literally just because Xerxes like, we need to focus on this. So I literally just took his advice, did a calculations, David assigned me homework. I go through the homework and everything. That's like, what if I took this literally? It seems to line up very nice. The other thing that gives me some notion that maybe there is some there is because literally by their definition, by the Wolfram definition of maximum entanglement for a maximally entangled observer, you have minimal energy divided by minimal time, which is just going to give you maximal power output. Blank power. Yeah, because that's the thing. It's like, yeah, you have a scaling factor that you're using to reduce those down to some minimal component, some sub-Planckian thing that does it exist? Maybe it does. I mean, one would think that there's something below this. We just don't know what it was or what it might be. The thing is, when you use that scaling factor for the Planck power, it didn't make sense when you're taking the square root of it because it ends up being like 10 to the minus 4 watts, which is something well within our realm. Um, you take the non-square root and use that as a scaling factor, yeah, it's ridiculously small. So that's why I didn't include it in my paper because it didn't seem to line up quite well. But yeah, no, take it is Planck energy squared. That's what it has to be because if it's going to literally be if this is literally Planck energy divided by that equals temperature, then that whole thing, if it's going to give you out this and you're just taking the square root, that's that's going to be what it is. Now, why is that even? Huh. So taking a step back before we go in radical. Coincidentally, this has a known interpretation. These units, even though it's energy squared, have some interpretations. I have not spent nearly enough time. I literally looked at one of these for extremely short. Okay. Quadratic Casimir operator of the Poincare group. What the heck is that? All right. The Poincare is something transformations in. Hey, I actually totally forget. It's about something about circular energy squared. And to be fair, in the original, or I think in Einstein's paper, it said that things are just expressed literally in energy squared. So operators for the total momentum squared, and the operator for okay. Uh, okay. So as first defined, it is a 10-dimensional, not a billion Lie group that is important to the model to understand the fundamental basics of physics. I always forget what this is. Okay, so something's non-commutative, a Lie group, all right. 10-dimensional. Consists of all coordinate transformations of Minkowski space. Or if everything were shifted 5 turns 60 degrees. 60, wait a second. 60 degrees? Okay. I believe I've read through here for once. Okay, hold on. The 10 generators and four space-time dimensions. And if I notice there, thank you. Thank you, Emmy. The 10 conservation. Okay, one for the energy associated translation through time. Three for the momentum. Okay, that makes sense. The transfer space measure. Three for the angular momentum. Okay. So energy is a single dimension. So momentum, it's like, all right, you got your X, Y, Z axis. It's like, all right. So you could be going this way, but you're also going kind of this way. Okay, so you got to translate. Okay, it's for your coordinates. Okay. Three for the angular momentum. Okay, so you could be rotating in a particular way. And three for quantity involving the velocity of the center of mass associated with hyperbolic rotations between each spatial dimension and time. I don't know what that means, but it reminds me of what Thad's been talking about for a while. The terrifying thing is, I mean, this sounds very right to me. And again, I'm also very biased. I'm not saying I don't know what all these things are. Uh, why is it 10? I don't know. I I may have an interesting clue. Now again, this is not a clue because I have some broad understanding. I literally just go through so many arbitrary computations, asking Wolfram Alpha questions. Then again, so many of them don't go anywhere. Going through and again, if you just the amount of screenshots that I have about arbitrary things that I'm like, I have no idea, but all of a sudden I get zapped by I don't know, Planck energy from a dust mote or something like that and completely vaporized. To be fair, my computer would probably be gone too, but uh, who knows if there's anything there. Uh, that is interesting. That is interesting. All right. All right. Have fun, David. I might pop over for what is it? What they do, the little nip and nag, little puppet show. Uh, well, is it math making me high? It could be many things. I mean, I'm not going to discount those factors. There's a lot of them. Does Planck temp give me the munchie? I'm pretty sure the temperature itself would make much of those munchies extra tasty, crispy. And by that mean they'd probably vaporized. Now let's go back to our Planck temperature. So, and again, it depends on how you want to set these things up. There might be better ways to do them than others, but anyway. So, okay, and a lot of times, if you see things about the Planck scale, very often people think, "Oh my God, ridiculously small." Do observers like us? Planck time, 10 to the minus 44 seconds. Planck length, 10 to the minus 33 meters. Yeah, yeah, those are ridiculously small. However, speed of light, it's, hey, maybe you run 10 kilometers an hour. Walk, whatever, maybe a brisk walk, maybe you're going 10 kilometers an hour, something like that. Yeah, the speed of light's like 10 to the 8 meters per second. Like 100 million, what is it? Like 180,000 miles per second or something like that. 186,000, something like that. I just remember learning that thingy first. You're like, all right, that's ridiculously fast for somebody like me to comprehend. Okay. But it's at least hinting at within physics as we know it, there seems to be a limit. In particle physics and cosmology, again, it's just from Wikipedia, take it from what's worth. The Planck scale is an energy scale of around 10 to the 28 electron volts. The Planck energy. The corresponding energy equivalent of the Planck mass, which is 10 to the minus 8. Now, when expressed in joules, the standard form of energy, uh, basically we got 10 to the 9 because there was like 16 orders of magnitude difference there. Uh, the difference between a joule and electron volt is like another blah, blah, blah. Hold on. Joule. It's like 6.242 times 10 to the 18 or something like that. Okay, I looked at this and okay, 6.242 times 10 to the 18 electron volts. Okay, so that's why it's so many orders of magnitude, and that confused me a lot before. Basically, because this is the amount of electron volts, blah, blah, blah. I totally forget the convert. What is all you need to know is 10 to the 7 ergs. If only we didn't appreciate the ergs and the emus and stuff, maybe we'd have a. Uh, and again, this is just interesting numerology. You would need to have a coherent theoretical framework to explain what's going on, hopefully with less inputs and more explanatory power of the observed phenomena of our realm. Might that exist? It might totally exist. And to be fair, if you happen to be a believer of perhaps the Everett interpretation, where you can have some infinite number of multiverses or stuff like that, yada yada yada. Um, Apparently, in one of them, this is already solved. So, I mean, if we're personally to me, I love the many worlds interpretation. It makes me feel so much better about myself because I just remember when I was 10 years old, and it's like, oh my God, how the heck do I justify all the things I didn't do? Well, maybe there's exists some reality where I did all the things, and I just use it as a coping mechanism to try to justify my own failures. You grow up and you find out, wait a second, there's a scientific framework that says this is a thing anyway? The thing that I just came up with just as a random way to cope with my failures? Cool. I mean, that sounds very engaging. Is that reality? I don't know. If we believe the Schrodinger equation is the answer, that is the way things are. Quantum mechanics is not complete. Maybe it's not. I can't say. Not a god or prophet. Just a dude on the internet. Uh, okay, I'm going back. I need to go to college. I need to go back to college and learn all these different things. Ah, jeez. Yeah, well, it's this is so hard. Yeah, yeah, about one 1 point. Is it 1.4? Okay, sorry, I was looking at that number. Yeah, about 1.4168 times 10 to the 32 Kelvin. It's a form of energy. It's a form of energy. Now, what that energy is doing is measurement of vibration of atoms or particles, whatever those things may or may not be. Okay, well, it's oscillation, and then we measure temperature, but it's photons, and that's an electromagnetic effect. It's how should we parameterize it? Or maybe is there perhaps more than one? I don't know. It's just interesting that this is squared. Um, let's go back for just a moment. Right, this energy squared. All right. So the quadratic Casimir opera Poincare group. All right. So that has some notion of something four. It's quadratic. So the quadratic Cauchy coefficient. Wait, was it saying the same thing? Okay, no, that's something different. Same thing. Electron. It's squared. Uh, Go back over here. Cauchy. Cauchy. Cauchy Euler. Oh. In optics, an parallel relation between the fractal radiance radiating like light or a particular transparent. Or simply Euler's equation is a linear homogeneous ordinary differential equation with variable coefficients because duh, all right. It's sometimes referred to as an equidimensional equation because it's particularly simple equidimensional structures. In mathematics, especially in topology, equidimensional equidimensionality is a property of a space that the local dimension is the same everywhere. Huh, that's interesting. Okay, so that's all at one. They're gonna have variance. All right. One. So that okay, so this is something about looks like divergence. Oh, interesting. Okay. We go back one more time. Because I clicked on this because this caught my eye, and I barely spent any dang time on this. The quadratic Higgs coefficient. I think this is actually in the standard Higgs equation there. They didn't have it laid out like this, but they had it laid out as I just remember a bunch of very, yeah, they had the mass term in there squared for the Higgs boson mass. They had stuff like that. But yeah, you get things like that, that it's negative, which is interesting. Also gives you this number, which, to be fair, if we take the square root of this, is also going to give us an imaginary something. Yeah, it's giving us imaginary stuff too. Yeah. Wait a second. That looks like kind of close to. Okay, never mind. Okay. This is complicating everything. Look at this. It's giving us imaginary things here. Why does this have to be negative? I don't know. I don't know what it means. I'm pretty sure this is why. To be fair, when I do it, well, it's comparison too. If you're gonna set up, you're gonna try to solve for the Higgs boson mass, and you just do. You're gonna solve for x. So like x x kilograms divided by Planck mass, square the whole thing equals h bar over joule seconds. Now again, this is very sloppy. I got a mass over a mass and a squared saying the whole thing is equal to the elementary unit of action divided by its reference of action. How do I just? I'm literally just doing that because that's what's necessary to get it down to no dimensional thing. Gives you this thingy, and no, it does give you a positive and negative solution. And actually, I think if I do it this way, I have no idea the mathematical reasoning for this. Maybe it's more specific, but as soon as I put brackets here, I think it's going to give me four answers now. Yeah. Oh, no. It gives me a whole bunch of them. Eight, one, two, three, four, five, six, seven, eight. Okay. Give me four negative and four positive roots. I don't know. Do you need your Higgsino or something like that there? Does this even make sense? Is that? I don't know. That's why I kind of like the Eugene notation. I still got to include both of these just because I don't know what the answer is. I don't got the answer. I'm just a dude, so it's I just throw this stuff here. Oh, sorry. Like our Planck constant, we're gonna take the square root. You wanna take the square root of that? Yeah. At least what CMS put in its most recent April publication, they had a target of 125.38 GeV divided by c squared. For the Higgs boson mass, when you put all the code out of stuff, it's actually for this estimate here, this Planck boson Joule conjecture, call it whatever you want. I don't really care. Um, it ends up being 125.376 with an uncertainty of 2 in that last digit of 6 there. Uh, so to be fair, it matches until we get to the error there. Uh, Maybe that's over data fitting, but it's just tuned to the dimensionless magnitude of action by the square of this relationship. So what it actually means, if there was some there, yeah, well, maybe it's a clue. I hear a lot of smart people saying we can try to figure out the hierarchy problem. It will give us some clue to what might be going on about our missing 17 layers of reality. Oh, look, 10 to the minus 17 in respect to the Planck mass. Those are missing layers of reality. I don't know. Okay, that's all for now. I've deviated. I've deviated far too far much, but essentially, the Planck the Planck temperature is, according to our calculations, the maximum limit of temperature. It's a lot of great videos you get, like Physics Explained. A bunch of other folks have done things on the. Actually, let me link that video because that is an amazing video. Because they comes at it from another mathematical way. It's like, all right, you're gonna have a particle and you're gonna combine it to something, and there's some form of oscillation there, and you're putting it in a minimum box. At that point, it's going to be oscillating so much it would effectively have a temperature of the Planck temperature. Because you'll hear these things about we had a spacecraft that was going around the sun. It it was exposed to 1 million degrees or 10 million, or something ridiculous in temperature. Like, oh my God, what happened to it? Basically nothing. Why? Well, that was like one photon. Okay. A single photon at a particular wavelength that happened to be that. Okay, it had that temperature for that frequency. It's were there lots of other photons? No. And yet I see Rick is commenting it's our randomized energy. Well, it's about particle vibrations and oscillation. That seems to be just kind of a randomization, or some may say a stochastic version of what's going on. Maybe. Yes, the other interesting thing. This is something that hold on, brings back. Uh, okay, when Thad started laying out things, it's like, all right, you got your Planck time, your blank length, your blank charge, your blank mass, your blank temperature. There is an interesting thing about these things. The minimum time and the maximum temperature. Time, temperature. This is the exact same thing, except big G and C are swapped off. Hmm. The only difference there is flipping the places of big G and C, but that's just the Planck power. And it's inverse because C raised to the fifth divided by big G. If it's to the fourth, it would be the Planck force. This is the Planck power. And then invert it. You get inverse power. Oh. Okay, I'm not actually, I knew that it was literally just the inverse there. It was basically big. Okay, so this is inverse power. This is called power. Called action. Okay, so inverse power like that. Over 4 seconds. Yeah, the only added additional component there is literally just Boltzmann's constant squared, and we're throwing it in squared there it, because we're just taking the radical. We we're just putting it in there to get it to work, right? That seems to be what we're doing. I mean, I hold on. Let me go to the Physics Explained video. Give me like been on a little bit of an alien binge if you couldn't tell. Here we go. This is a great video. In my opinion, again, take it for what it's worth. But if someone would like kind of a deep dive, and again, it's less than half an hour there. It's got a lot of pretty pictures and everything, and things that a lot of folks can. Hey, yes. Be wary, my friend Poindexter. If you say Planck too many times, you might summon. I don't know. It's oh God, would it be Planky? Would it be the equivalent to Clippy? God, I hope not. I just feel like maybe they should do this. It's personify Max Planck into some I don't know, some I don't want to really say erudite, but some sophisticated piece of piece of wood or cutlery, maybe a monocle or something. Oh, I'm terrible. Those temperatures. Okay. So this has been very useful. You look at things, you do calculations, but then all of a sudden someone says something. It's like, wait a second. It's like, have we ever measured these things? Like, oh, let's look at that. David gave me that thing. It's like, yeah, I don't think we've ever measured the electric charge of a black hole. We basically just measured the electric field of the Earth within like the past year or so. And again, maybe that's a selfie problem, but yeah. But as we learn more, we're going to be able to get better precision, like better measurements, and then help continue to refine our physical frameworks for reality. And as we refine our physical frameworks, we should be able to have the proof in the pudding, i.e., hypothetically, if you have a coherent theoretical framework and your modeling matches experiment, let's say your model holds water, so to speak, then you'll be able to craft new and exciting technology. As we craft new exciting technology, hopefully a lot of the problems that we have created from ourselves will be able to superpass, so to speak, and be able to do a lot more cool, interesting things, and more useful as well. And if people still have problems with each other, in my opinion, we could just let them get into the ring, engage in mortal combat of the doctrine of bodily autonomy, because if something is so important that you must quote unquote destroy somebody, I say we let them fight. Consenting adults facing consenting adults. I mean, unless they're talkers. I mean, again, there's nothing fine. I'm a talker. I do a lot of talking. I'm just saying, if you're a true believer and you must vanquish evil, then you're at least willing to legally get in the ring and potentially eat a knuckle sandwich for something you truly believe in. Otherwise, you probably don't truly believe in it. Now that we've affected everybody, or offended everybody, hey, Mark, good to see you, my dude. Good to see you. Yes, yes. On and on, my friends. But that's what we've got going on. Going to be sharing. We might be breaking the multiverse with Fizz if she's around tomorrow. Other than that, there's going to be some interesting things that I'm now allowed to talk about. Full disclosure for those of you that have tuned into the end of the stream. Uh, I went to MIT's foundational thinking. No, bleh. Oh, I'm blurring things out. I'm crossing projects. I went to MIT's Human Augmentation Lab demo on Saturday. Ran into a bunch of interesting folks. I ran into actually my friend Tyler Goldstein, who was friend of the channel, had on before. Wasn't expecting to see him. I ran into Stephen Wolfram. Kurchai Mungal was there. Bunch of folks from either the Wolfram Summer School mentors. I saw Dugan. I saw Phileas. Uh, I saw Olga from one of the other previous schools. And one of the reasons we were there is that I may or may not be involved with a small side project. Steven has so many different side projects, and occasionally he's publicly said he likes to collect interesting folk and see if there's interesting directions and things that they can do. And I may or may not be one of those folk. Um, Basically, there's a project that's going to be available to folks that might not be able to take 3 weeks to a month out of their lives to go to the Wolfram Summer School, which is going to be rebranded and under different things and stuff now. Uh, there's going to be opportunities for folks that would like to learn, potentially contribute, and probably do some networking. And we'll be talking about that a little bit later, since we now have the okay to publicly talk about it to gauge some public interest. Uh, but that's all I got for right now. So, hey, take care of yourselves, everyone. It's a wacky wild world out there, but it looks like there's some new and interesting things just around the corner coming. So, other than that, peace out, everybody. Catch you next.